Hi, I'm Krutika Shahare. Today we'll be talking about biodiesel production and combustion. As a brief introduction, biodiesel is a domestically produced, clean burning, renewable substitute for petroleum diesel. It is a fuel produced from various feedstocks, including vegetable oil, animal fats, or algae. It is an environmentally safe and low polluting fuel for most diesel internal combustion and turbine engines. It is because of the growing interest in search for alternatives to petroleum-based fuels that capital investment into small-scale biodiesel production facilities are starting to take off. Some advantages of biodiesel include that it is easy to use and no vehicle modifications are required. Power, performance, and economy are highly enhanced with an added benefit that emissions of greenhouse gases is reduced to a large extent. Surprisingly, less toxic than table salt, biodiesel has minimal environmental impacts. We divide this presentation into three segments. The first gives an idea about the method of producing biodiesel. The next segment shows the construction of a commercial flow sheet to simulate large-scale production in Aspen Plus. Lastly, we associate this process to heat transfer and analyze new initiatives in the production of the same. The production of biodiesel includes the transesterification of methanol and catalyst sodium hydroxide along with pre-treated oil and fats. Transesterification reaction produces two products, glycerol and fatty acid methyl ester, also called FAME. This is then refined and purified into biodiesel fuel, and the secondary product, glycerol, is commonly used for soap production. The molar feed ratio of 6:1 is used for methanol to triolene, and the process occurs at 60 degrees Celsius and 58 psi pressure. To prevent saponification, we use fresh water to wash the glycerol from the biodiesel product in the first decantation stage. Biodiesel burns 75% cleaner and generates 93% fewer hydrocarbons on burning. It also creates 80% fewer cancer-causing polycyclic aromatic hydrocarbons, PAH. Additionally, biodiesel can be synthesized from a variety of different feedstocks of fatty acids. However, all of this also has limitations. The major ones are the cost of refining the biodiesel and production capacity. Furthermore, it is difficult to achieve 99.7% FAME purity and proper viscosity as a compliance standard set forth by some regulatory agencies. Next, we will show you the process of simulation on a commercial scale in Aspen Plus.
I am Hemant and I will walk through the Aspen analysis process. These are the components involved in the reaction of the Aspen Plus simulation. This is my oleic acid methyl ester, this is triolic acid and fatty acid methyl ester, and this is my methanol. How the transesterification reaction of triolene in the R-stoic reactor takes place. In the R-stoic, triolic acid react with methanol to give oleic acid methyl ester and glycerol. Here we assume that 95% of conversion of the oil takes place in the R-stoic reactor. This glycerol is my secondary product and oleic acid methyl ester is my first product. And these are the general unit operation used in the biodiesel process. And why we transesterification reaction used in the R-stoic reactor? Because in transesterification reaction, oil reacts with alcohol in the presence of catalyst to yield the biodiesel and glycerol. And the methanol recovery. The methanol recovery takes place after the reaction where in the R-stoic reactor, where we can use maximum methanol to recover out in the initial feed. FEM purification generally takes place in my LLE extractor and after this catalyst removal in the R neutralization reactor. And these are the equipment specification used in the flow sheet. Basically for transesterification, we use R-stoic. For methanol recovery, we use red flag distillation column. And for catalyst removal, we use R-stoic followed by the red flag column. For FEM purification, we use red flag distillation column, and water washing, we use LLE. In this my feed stream, my FEM and methanol, these are my main product. And after this, how we can separate FEM from the glycerol. Here we use water washing for the separation of FEM from the glycerol. This is my H2O, where FEM washing takes place with the help of H2O. In this stream, my FEM, my maximum product is FEM, and in this stream, my water and NaOH is my maximum product. In this R neutralization reactor, we use H3PO4 for neutralizing NaOH, and the glycerol is also the product of this reactor. In this reactor, we can use red flag distillation column for the recovery of the glycerol, and this is flash for the recovery of FEM from the water. In this purge stream, my maximum amount of water recovered, and this water we can use here in the R neutralization reaction for the neutralization of the NaOH. In this stream, we pressurize FEM for the my desired final product. In this distillation column, this is my red flag distillation column, where we use the distillation of FEM for the other products, and this is my final stream where the my desired product of FEM is coming out from the red flag distillation. These were the final results of this simulation, and we can see that the FEM we get in that stream is 2.31 kilomole per hour, and all the other stream in the comparison of the FEM are very less. These all are the tables of the stream table that we generate from the SPEN plus.
So all this process requires biofuels to evaporate and then separate. So, and when we talk about biofuel combustion, what comes to mind? It evaporates and catch fire. But the thing is, we don't focus on main processes that goes on in evaporation and mass transfer. When a droplet is evaporating, several processes happens, and two of them are main: transient heating and mass diffusion. And there is a convective mass flow of gases which carries that evaporated fuel vapor and carries it to the combustion chamber of the engine. Here, three main processes occur, and this can be modeled into three submodels uh, following: gas phase model, liquid phase model, and droplet dynamics. In gas phase model, the model involve mass vaporization rate from free surface and the heat penetration into droplet via external convections. Here we quantify how much heat we are giving and how it affects the surface and the droplet temperature. In the liquid phase, we quantify for liquid fluid flow inside the droplet droplet fuel, and there is a free flow inside the droplet of fuel. It occurs due to the differential heating of surfaces, and in the gas dynamic phase, we we update size and the velocity of the droplet fuel, and we can model this model, and these are the assumptions we take. The droplet is considered to retain its spherical shape at all time of the process, and the temperature, for simplification of process, we assume that the temperature of droplet surface is same at any point of time, and these are the steps involved. We first quantify molar and mass fractions of the fuel at the fuel surface, and then we calculate the Reynolds number and Nusselt number and Sherwood number, which are variable, and we have to quantify them from turbulent flows. In next, we calculate Spalding mass transfer number (BM) and diffusion film thickness correction factor (FM). Also, we have to calculate modified Sherwood number and vaporization rates. Following that, we also need to modify Nusselt number because it's a turbulent process, and uh, it changes throughout the process. And also, since the environment is of a carrier gas, so every quantity like Reynolds number changes with time. We balance the energy, and then with energy and there is mass transfer occurring at the surface of the fuel droplet, and we since the temperature is changing, and when the temperature of the surface reaches the evaporation point of the fuel, it evaporates and the diffusion occurs outwards. So in this manner the radius of the drop decreases with time, and we can quantify this uh, radius of biofuel from these equations. And again we can update this radius, and we can calculate the time for a droplet to evaporate, and we can write a MATLAB code for it, and then we can quantify the all processes and the temperature of surfaces. And this can help us to model engine designs and combustor designs, so we can increase the efficiency of both. In this project we took some new initiative, like the raw materials like methanol, ethanol for biofuels obtained from corn grains, so we can make a better biofuels from the switchgrass, sugar cane, sweet sorghum, and and other things which contains more cellulose. If biofuels are future, so and since it's considered renewable sources, so we should be more focusing and uh, dedicating ourselves to improvise the biofuels. So on next slide contains the supporting data for our use of grasses like switchgrass and sugar. Here we can see the component and how much we can get from a the how much we can get from a normal corn grain and switchgrass and sugarcane, and we can actually quantify this and use them as raw materials for biofuel productions, and increase our efficiency and decrease our cost both at the same time. We conclude this project as complying that biodiesels are the need of the future, and we provide useful description for the process for the plant wide production of the biofuel. And following slide contains the nice video on biofuels we found on YouTube, so have a look at it.
Biofuels. Biofuels are combustible fuels created from biomass. The term biofuel is usually used to describe liquid fuels such as ethanol and biodiesel that are used as replacements for transportation fuels like gasoline, diesel, and jet fuel. Ethanol is an alcohol formed by fermentation. It is used as a replacement for or additive to gasoline. Biodiesel is an oil produced by extracting naturally occurring oils from plants and seeds. Biodiesel can be combusted in diesel engines or blended with diesel fuel. Biofuels are grouped in 3 categories based on the type of feedstock used to produce them. First-generation biofuels are produced from food crops. For ethanol, feedstocks include sugarcane, corn, maize, and others. For biodiesel, feedstocks are naturally occurring vegetable oils such as soybean and canola. Second-generation biofuels are produced from cellulosic material such as wood, grasses, and inedible parts of plants. This material is more difficult to break down through fermentation and therefore requires pre-treatment before it can be processed. third generation biofuels are produced using the lipid production from algae. In addition, the term advanced biofuels is used to describe the relatively new technological field of biofuel production that uses waste such as garbage, animal fats, and spent cooking oil to produce liquid fuels. Biofuels are currently the only viable replacement to petroleum transportation fuels because they can be used in existing combustion engines. This is an increasingly important advantage with growing concern about the environmental impacts of fossil fuels around the globe. Biofuels can also help provide energy security in regions that do not have hydrocarbon resources but do have suitable agricultural conditions. While there is some dispute over just how renewable biofuels are, it is generally accepted that the crops used to produce them can be replenished much faster than fossil fuels, which take millions of years to form. Concerns about biofuels are usually centered around the fact that they are an agricultural product. Producing these biofuel crops can mean competition with other natural resources, particularly land, food, and water. First-generation biofuels use only edible crops, which has led to biofuel crops displacing food sources in certain regions and subsequent spikes in food prices. In many regions of the world, subsidies are provided for these crops, which only amplifies these issues. In addition, increased agriculture of any form comes with concerns of deforestation and biodiversity loss, as well as water and fertilizer use, which have environmental and climate impacts all to their own. That's biofuels.
So here are the group members: Hemant Nagar, Krutika Shahare, and I'm Neeraj Gupta, Nitish Yadav, and Siddharth Ganeriwala. This project is for course CHE312. Instructor is Dr. Raj Ganesh Pala of IIT Kanpur. Thank you.